We can use everything we learned about our first and second derivatives to help us sketch the graph of any function. So in order to sketch the graph of any function, what we're going to want to do first is figure out what's the domain of that current function. Then we want to find the x and y intercepts of that function, determine the intervals where we're increasing and decreasing, and the local extrema. All of that's done using the first derivative. And determine concavity and inflection points, all of that using that second derivative. And then plot all the information on a graph and sketch it. So let's take a look at example 6, which is asking us to summarize the pertinent information obtained by applying the graphing strategy. So the first thing that we're going to want to do is find the domain. Well, x minus 3 times x squared minus 3x plus 3. Well, when I multiply all this thing out, this is just a polynomial. So any polynomial has a domain of all real numbers. So the domain of this function is all real numbers or negative to positive infinity. Step 2 is asking me to find the x and y intercepts. Well, for my x-intercept, what I need to do is I need to set the function x minus 3 times x squared minus 3x plus 3 equal to 0 and solve for x. Well, I know I'm allowed to set each one of these individually equal to 0. For the first one, I get x is equal to 3. And for the second one, x squared minus 3x plus 3 equals 0. Well, that doesn't factor, so I can always use a quadratic formula to solve it. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So x is going to equal 3 plus or minus the square root. Here I'm going to have negative 3 squared is 9 minus 4 times 1 times 3 is 12 all over 2. So then x is equal to 3 plus or minus the square root of negative 3 all over 2. And if it's an imaginary number, that means no x-intercept. So my only x-intercept is going to be x equal 3. My y-intercept, you find a y-intercept by finding f of 0. So 0 minus 3 times 0 squared minus 3 times 0 plus 3. So here f of 0 is going to be negative 3 times 3, or negative 9. So my y-intercept is going to be at 0, negative 9. So step 1, find the domain. Step 2, find the x and y intercept. Step 3, determine your intervals of increasing and decreasing. So recall the function f of x is x minus 3 times x squared minus 3x plus 3. So if I want to find the derivative, well, there's two things that I can do here. I can either distribute first, or I can use my product rule to find this derivative. I'm going to go ahead and use the product rule to find the derivative. So I'm going to label this guy my first and this guy my second. And remember, the derivative of the first times the second is always going to equal the first times the derivative of the second plus the second times the derivative of the first. So, in our case, f prime of x is going to equal the first times the derivative of the second. Well, the derivative of the second, x squared minus 3x plus 3 is 2x minus 3, plus the second, which is my x squared minus 3x plus 3, times the derivative of the first. Well, the derivative of x minus 3 is just 1. And if I clean this up, f prime of x is going to equal, well, if I FOIL this out here, x times 2x is 2x squared, x times a negative 3 is negative 3x, negative 3 times 2x is negative 6x, and negative 3 times 3 is plus 9. And this is going to be a plus x squared minus 3x plus 3, because anything times 1 is itself. Combine your like terms, and you end up with 3x squared minus 12x plus 12. So that's my first derivative. So I need to figure out where is this thing equal to 0 and where is it undefined. So is there any place where it's undefined? Well, no, because the first derivative is a polynomial, so there's not going to be anywhere where it's undefined. So I need to set 3x squared minus 12x plus 12 equal to 0 to find my partition numbers. I notice here I can divide all this by 3, and I get x squared minus 4x plus 4 is equal to 0. Then this factors as x minus 2 times x minus 2. Since it's the same number, I just need to set it equal to 0 once, and I get x equal 2. That's my only partition number. So then I draw my number line. The only number that I write on that number line is the number 2. And then I pick the test points. From this section, I'll pick the number 0. And from this section, I'll pick the number 3. And then we need to figure out what's happening to the first derivative at 0 and what's happening to the first derivative at 3. So we're going to plug it into this one right here. So grab a calculator, and we end up with 3 times 0 squared minus 12 times 0 plus 12, which is 12. So that's a positive number, and since it's a positive number, that means that in this interval I am increasing. And then plug in a 3. So again, I'm just going to hit second and then enter, and then change all my zeros into 3s. And I get the answer of 3. Well, 3 is also a positive number, so I know that in that interval I am also increasing. So what does that mean for me? Well, that my function is going to be increasing from negative infinity to positive infinity, and it's not going to be decreasing at all. And I also know it has no local extrema. How do I know it has no local extrema? Because if I'm increasing and then increasing some more, I'm never changing from increasing to decreasing, which means I have no local extrema. So then I'm going to determine what my second derivative is so that I can find my concavity. So if this is my first derivative, then f double prime of x is going to be 6x minus 12. I have to figure out my partition numbers again, and those happen where the second derivative is equal to 0 and where that second derivative is undefined. Well, is there any place where the second derivative is undefined? No, because it's a line, so it's defined everywhere. So we're just going to set the second derivative equal to 0, and solving for x, I get x is equal to 2. So same thing here, I draw the number line. The only number I put on that number line is the number 2. Then I choose the test point between negative infinity to 2. I will choose 0. And then from 0 to positive infinity, I'll choose 3. So I need to figure out what happens to the second derivative at 0 and what happens to the second derivative at 3. So we're plugging it into our second derivative. So just grab a calculator. So we are going to say 6 times 0 minus 12, which is negative 12, which is a negative number, which means that in this interval we are concave down. And now we're going to plug in the number 3. So 6 times 3 minus 12, and we end up with a positive number, which means that in this interval we are concave up. Since we are changing concavity, we're concave up from the interval from 2 to infinity, and concave down from the interval negative infinity to 2, we will have a point of inflection. And our inflection point will happen at 2 comma. Well, remember, in order to find the y value, plug it back into the original. So this was our original. So plugging in a 2 there, we would say 2 minus 3 times 2 squared minus 3 times 2 plus 3, and we'd end up with negative 1. So our point of inflection is at 2 comma negative 1. And then we're going to put all of this information together, and we're going to put it on a graph. So I'm going to summarize all the information that we have before we graph this. It's just because we can't see it anymore because I've scrolled. I'm going to write down all the information we gathered again. So remember, the domain of the function is negative infinity to positive infinity. My x-intercept was at 3. My y-intercept was at 0 comma negative 9. I'm increasing from negative infinity to positive infinity, and I'm decreasing nowhere. I have no local extrema. I'm concave up from 2 to positive infinity, and I'm concave down from negative infinity to 2, and my inflection point is 2 comma negative 1. Now if I were to draw just number lines to represent all this real quick, so that I can know exactly how to draft this. So if this is f prime and this is f double prime, this is 2, I know I'm increasing and increasing. And for my second derivative, I know I'm concave down and then concave up. Well, recall, anytime you are increasing and concave down, you look like the left side of the letter N. And anytime that you are increasing and concave up, you're going to look like the right side of the letter U. So putting that all together, let's plot these points on a graph. So again, the point 3, 0 and 0, negative 9. So 3, 0. And 0, negative 9. And the inflection point of 2 comma negative 1. And then I know all the way to 2, I should be increasing and concave down. So all the way to 2, I'll be increasing and concave down. And from 2 to positive infinity, I should be increasing and concave up. There we go. So that is the graph of that function x minus 3 times x squared minus 3x plus 3. That's it for section 4.2.